Welcome everybody to geohug, and today is going to be such a good one. I am thrilled that we have Grant Rocky Osborne joining us today. So Rocky is a highly respected geologist with over 40 years of experience in international mineral exploration and underground mining, with particular expertise in nickel and gold. He's been involved with a number of discoveries in Brazil and Australia, such as the Rockies Reward nickel mine in WA and the C2C zinc copper silver deposit in Brazil. And since commencing his consultancy in 2014, Rocky has been engaged by a diverse range of exploration and mining companies, providing guidance and oversight to exploration programs across a broad spectrum of commodities. So with his expertise, it is going to be brilliant learning today about context is everything, nickel exploration with the advantage of hindsight. So this is going to be an awesome session. I hope you all enjoy it. I'm very honored that you're here. But yes, we will be opening up the floor at the end. So I'll start promoting you up as a panelist. Please don't be shy. Come on through and we can have some great discussions at the end. But yes, thank you so much, Rocky, for being here. I'm honored to have you here.
No problems.
I was curious before we get stuck in, what got you into geology to begin with?
My reason for becoming a geologist is similar to many others that have been on before. When I was in my very final years of primary school, before going to secondary school, I had an 11-year-old friend who took me to his parents' house and showed me his rock collection. And once I saw that rock collection, I was pretty much hooked. And I decided I have to try and find out a way of becoming close to the rocks and collecting more rocks. So that was the reason why I became a geologist in the first place.
That is awesome. Do you remember what rocks it was that really got your interest?
No, it's a little while ago. Jess, I can't remember that far. I remember they just all looked nice and shiny, and I thought that's nice. Some shiny rocks would be nice, and I could do with that.
That's perfect. I love that. And you've done so much. You've worked in like so many regions. You've been involved with discoveries. I'm very curious, what are some real standout highlights in your journey so far?
I had to think a bit about what to say on this one here, because there are a number of things that are of interest. But without doubt, and the biggest career highlight in my life was the discovery of Rocky's Reward. The discovery of Rocky's Reward came when I was very young. I was 26 years old when I found the deposit, and it subsequently has been a major cornerstone to my career and a stepping block to getting places and meeting people and doing other things. So that was in 1984, so it's a long, long while ago. Second, in terms of just sheer awe for what geology can bring and what the exploration science is able to offer geologists, was a visit I made in 1993 to the Norilsk-Talnak nickel camp in Russia. And just to go to Russia very early, just after the Russians had actually opened to Westerners, and to visit the mine and go underground and to stand in a stope that was 25 meters high of massive nickel sulphide is very, very awing. You look spend all your life trying to find these things, and you find them in drill core of 2 centimeters, 10 centimeters, a meter or two, and you get pretty excited. When you go to Norilsk and stand in a stope which is 25 meters high and it's all massive sulphide, and the ore is so valuable that each cut is completely filled with concrete, so they can keep moving up. It just takes your breath away, and you realize that there are some things in nature that we have to respect as being very major events. And the third thing that I really would like to highlight in terms of a career highlight is actually working with a number and many varied multidisciplinary teams on discovery and on understanding ore systems. And I'll speak to one of these in the talk, and that's the discovery of, or not the discovery, the development of the Jaguar hydrothermal nickel deposit in Brazil, because it's a new style of nickel deposit and it's been very, very stimulating to work on.
That's amazing. What a journey you've had. It's no, I found it fascinating looking you up and researching you in the lead up to this. So it's yes, it's awesome, the journey that you've been able to do, and I'm very, very happy to have you here. I'm to the good bit. Pet rocks, what have you got for us today?
I have 2 pet rocks, Jess. I'll show one initially now and then one at the beginning of my slideshow, because it's a bit small to show on the camera. So the first pet rock is here.
Mm.
Hopefully you can,
Yeah,
you
can see
what
that.
you can see, what it is, it's actually it's a little bit of massive or bit of lath textured or triangular textured ore from the Rocky Osborne nickel deposit. And the reason why I want to bring this into attention, and I'll show it to you, is that it has a very key importance in the talk that I'm about to give. So in the colors of the rock, the dark green blackish material is serpentinized olivine, while the tan triangular pieces and lath-shaped pieces are in fact nickel sulphides between the laths of serpentinized olivine. And I'll come to that in the talk.
Wow. Well, I'm very excited to hear from you and see a picky of the other pet rocks. So yes, if you want to share your screen and we can get stuck into it.
Okay, so pet rock 1, which is the one that I didn't show you because it's too small to go on the screen, is a little bit of jasper that was given to me by the first geologist that I mentored within the AIG mentoring program. And that's 11 years ago now. I've been doing it ever since. And it's just a little bit of jasper, but it's interesting in that jasper is thought to be a rock that gives you lots of strong feelings about life. It might be protective. It might make you more balanced. And I thought it was interesting because that was the little rock that my first mentee gave me in that time. Now I'll just move down to the next one, because what we'll see here is that what you see depends on the angle of your perspective. If you look at the photo that I've got in here, you'll see the little pet rock sitting on top of the box. But if you look at what I've outlined in the bottom, you see a pineapple. So they're both obviously the same object, but it all depends on the context and what you're talking about. So as a wise man once said, context is everything. Okay, pet rock 2 is one that I showed just previously. I have highlighted in purple here, the magenta color, the zone of the lath-shaped serpentinized olivine, and material in the middle that's the kind of tan color is pyrrhotite and pentlandite. That's the nickel sulphide ore from Rocky Osborne. These kind of textures, or these kind of things that you control in your mind, are called ore guides. And I'll get you to remember this shape because you'll see it a bit later on in the presentation. Okay, so we'll start the talk now. The first one was just on the pet rocks. Before I go into the talk, I would like to extend my great thanks to all of my ex-colleagues, both within BP Minerals and predecessor companies, Western Mining Minerals, BHP, Mirabella Nickel, Centaurus Metals, and also to the Brazilian equivalent of Amira, Dimbi, because these people have helped me in preparation of the talk and in fact of getting experience all the way through life. The photo on the right-hand side shows a very young me on the 19th of April in 1984, following the discovery of hole PT104, which was the 5th hole drilled at Rocky Osborne and the first one to hit massive nickel sulphides. In this talk, you'll see that I've in the examples, I've put the dates when I worked upon these deposits. And the interesting thing is that that covers quite a large extent of time, from the early 1980s right through to very recently. And the reason for putting the ages on there is to get people to realize that you're never too old to learn. As you go through life, you're always learning new things. And as I said in the header here, experience is the best teacher. So what I plan to cover is the reason why I've called the talk Context is Everything. Questions about how to know what is important and a sense of when you're getting close to the answer that leads to discovery, and a little bit about experience, and then I'll go into the 4 examples that I've got. So the first 2 are komatiite nickel sulphides from Western Australia here in the Yilgarn Craton, and the second 2 are from Brazil. The first of those being Santa Rita mine, which is a mafic-ultramafic nickel sulphide, and the last example being Jaguar, which is a hydrothermal nickel sulphide. And I'll finish the talk talking about some lessons learned. Okay, I've called the talk Context is Everything because as I've gone through life, I've began to realize that the more detail we get on a particular area, the further we get from actually understanding what those details mean in the larger context. And if you don't understand what the larger context is, then there is no way you're going to ever understand what you're trying to find on the small scale. So many others have talked about it before. Geology is a case of changing scale from very, very close detailed scale, zooming right out to the large scale context. And only by understanding how the two are related can we ever make any progress. So Context of Everything came from a book written by Alvin Gouldner called The Wildcat Strike, which is about a strike in an American asbestos mine. And Gouldner was a social scientist looking at the way the strike had happened and what happened with humans that were involved. And he realized that the only way that you could understand the behavior was looking at the context in which it happened. And that's pretty commonly recognized in the phrase there's a time and place for everything. One of the other authors went further by suggesting that ignoring context, we're just not being unwise, but downright stupid. And that, I think, is a very important point for geologists. If you forget the context you're sitting in, then it's not very, very good idea. And the key takeaway from this slide is what's in red. Nothing exists and therefore can be understood in isolation from its context. And that's why I think it's very, very critical that this kind of thoughts can be used in geology. Okay. Mysterious are the moments that must have brushed me with their wings and passed me by, when fate beckoned and I did not see it, when new life trembled for a second on the threshold, but the word was not spoken, and the might have been shivered and vanished, dim as a dream into the waste realms of non-existence. Now, why have I used this quote? Because I've found through life many, many times I'll be doing something and I get that little bell goes off and thinking, there's something here that I'm not quite seeing. There's something here that I need to drill down further into. And if I dwell on it and try and force it, then I've lost it, almost inevitably. In many cases, the thought I was trying to find will come back, but not in every case. So it's kind of like a deja vu moment. And my context is that these moments, if they can be regarded as moments of awe or inspiration, then it may in fact reflect intuition through the right hemisphere of the brain, rather than the clinical left hemispheric bias, which is what's favoured by society and which we've all learned through Western society. So intuition is a recognition of something experienced before, whether or not you can recall it or describe it. It's the sixth sense of knowing without knowing how you know, but it actually is the norm of mental life. My contention is that if we could capture and nurture the production of these instantaneous flashes and channel more right brain thoughts, we'll be more successful. And I recommend that you record the moment and revisit it so that your subconscious mind can keep researching within the cloud, or is that fog, of your brain. So when I say record these things, you just make a note of, I meant or was thinking about that, or a photograph or something, and just have it, because whilst you have a note of what you couldn't understand, as time goes by, you'll begun to understand it. Okay, this brings me to experience. It has been said that experience is the best teacher. Now, Anthony Robbins, who's a self-help author and motivational speaker, has written this law of experience, which I quite like. And it goes that success comes from good judgment comes from experience, and experience comes from bad judgment. So if you cancel out the redundant persons in there, what that actually means at the end is that success comes from bad judgment. So I think that's very good, particularly for young geologists, because what it's telling you is that it doesn't matter if you make an error. And in fact, the only way to get better and find stuff is to make lots of errors. So obviously you want to get into the habit of not making too many errors, but errors are in fact a very important part of the learning process and a very important part of experience, because that's how experience is built up. At the same time, however, you need time. Time really is an important factor in the whole affair. As Warren Buffett says, no matter how great the talent or efforts, some things just take time. For example, you can't produce a baby in 1 month by getting 9 women pregnant. So you need to have trial and try again, and continue to do it to have success. Okay, so now down to the examples. As I mentioned, the first two examples are on komatiite nickel sulphides in Western Australia. And the first one is from the Perseverance deposit. When I first worked there, it was called the Agnew nickel deposit, but subsequent to that, it's been renamed the Perseverance nickel deposit. I began work there as a mine geologist in 1981 until in 1984, when I became an exploration geologist, also on the same site. So, for those that are not aware of where the Agnew belt is, it's here. It's the northern portion of the Archean Kalgoorlie terrain within the Yilgarn Craton here. Perth sitting down over here. So we're about 700 kilometres to the west of Perth. And to zoom into this portion of the Agnew belt, we see that there are a number of nickel deposits in the red balls here, right up against the Perseverance fault. Perseverance is here. Rocky Osborne just to the north, Harmony and Sir Samuel, 11 Mile down to the south. So we're going to be talking about both the Perseverance and Rocky Osborne. This will be the first example, and this will be the second example. This slide is reproduced from a 1973 report and shows the interpreted geology at the 1350 metre level prior to underground development. At the time, the deposit was considered the type example of the intrusive dunite-associated nickel deposit class, with nickel sulphides deposited at the base of the intrusive dunite as thin, massive sheets overlain by thick, disseminated sulphide ore bodies. Note the faulted basal contact of the ultramafic and what was then called remobilised squirt sulphides up to 400 metres away from the main ultramafic body. This actually comes from an internal report by Australian Selection or Selection Trust, which was the joint owner of the Perseverance mine together with Mount Isa Mines. This 1984 slide, taken from a report that I wrote when I was a mine geologist, shows one of the lower levels from underground mapping. By this time, the effects of shearing of disseminated sulphides, locally boosting zones of disseminated sulphide in the stress shadows was evident and known, as well as the replacement of sedimentary sulphides by massive nickel sulphide that had replaced along the sedimentary horizons. In this case, it is an actinolite sulphide schist, probably a sedimentary sulphide that has come into contact with the nickel sulphide and has been replaced locally into the area. Note also that at that stage in the mine nomenclature, the zones between the massive sulphides or the ore bodies were known as noses. This is 1 nose, 2 nose, and 3 nose, and that will become important in the next section. So while I was employed as an underground mine geologist, I produced the first maps of the mine other than those used for grade control. So at that time, the mapping was entirely restricted to mapping just the ore production, and I went and mapped the rest of the mine just because I had interest in mapping it. At this very time, there was quite a heated debate regarding the origin and nomenclature of these vertical fault-bound slices and the associated rounded ultramafic sediment contacts, which are shown here in these convex noses. Were they in fact fold noses as proposed by Finlay in 1980? Were they in fact fault slices, which is the proposed that I had? And in fact, does it matter? You'll notice here I've got a little ringing bell. When the ringing bell symbol comes, these are the ones that I should have realised at the time was important. I realise it is now, but didn't then. So when you see those, you'll see that's a little reminder to me to explain what was going on. So this is a particularly good slide and a very, very good publication I recommend everybody should get a copy of. The publication itself is called The Importance of Incompetence. And it is by a 1992 geology paper by Talbot and Sukotsis, and it's a reminder to geologists consider both the metamorphic grade and the deformation history when considering the textures. The key takeaway is that ultramafics become incompetent relative to siliceous host rocks where primary olivine and pyroxenes are hydrated serpentine and amphiboles. and vicas when they deform at upper amphibolite or granulite facies. And the less competent parts of the rocks undergo foliation development and become sheared compartments, while the more competent rocks experience less shear and tend to become shortening. So what happens in practice is this. This is from the same publication showing exactly in the little key diagram here. This is the mafic body here, intruded into a granite in this case in here. And what you see is this series of cusps and very strong pointed shapes coming into the zone in here, and also larger or much wider cusps developed along the upper and lower contacts. Here's one of these lower cusps shown down in here. Now, I put it to you that what I was seeing in those fold nose at Perseverance is in fact nothing more than what's happening in here, the deformation of the much more competent ultramafic body within the very silicious acidic tuffs around the edges and development of strong foliation becoming sheared. So I should have perhaps thought about that, which would explain the reason that in fact aren't in fact folds, they are in fact deformation features. Okay, this is a 1994 interpretation of a lower level sill, also at Perseverance. And the important thing to note here are the areas that I've highlighted with the arrows. So these are what are termed matrix ore, and we'll come to about a little bit later on what the matrix ore are. But the matrix ore commonly forms in the sheared ultramafic, the position through in here, and on contacts here with barren talc tremolite chlorite rocks shown in the green in this section through in here. Now, these triangle ore are shown in these photographs here. This one in the middle, remember back to what my pet rock at the beginning, this is where it comes from. This is what you would see on the interior of that pet rock, and it's the same kind of texture you see underground. These are underground slides from underground drill core, and the one on the right is underground in a stope, looking at the face of the wall. So the sulphides are in fact triangular to lath shape because they're surrounded by metamorphosed or by serpentinized metamorphic olivine. The texture was first described by Martin and Allchurch in 1975. Okay, example 2 is just up the road from the Perseverance nickel mine, in fact 2 kilometres up the road from the Perseverance nickel mine, and I've used it to emphasise the importance of following up anomalies and appreciating structural overprinting in nickel sulphides. So this is a very old slide, 1984, showing the Rocky Reward Gossan before the deposit was discovered. Having said that, you'll notice the presence of a drill hole here, PT84. This is the collar position, and the collar position's obviously been the chips have obviously been disturbed in this area in here. This hole had in fact drilled under this Gossan, but had been left for 10 years without anybody doing any work on it, without realising the fact this was in fact an ore deposit. The two gentlemen showing in here, for those that might know them, are Martin Spence, an exploration geologist of BP Minerals, and Jim Martin, the exploration manager of Australian Selection. This drill hole, PT85, will come back further on. We'll see it further on in the talk. So when I left Agnew Underground in 1984 in January, I was told immediately that my next job would be as an exploration geologist at the same site. So whilst I lived previously at Agnew at Leinster, I was transferred down to Kalgoorlie, but then had to come back and work back into the single means quarters at Leinster as an exploration geologist. And I was given every single report that Australian Selection had all up the belt from Agnew all the way up almost to Mount Keith, and said, Rocky, start where you want. We want you to find a mine and you need to do it quickly. So I thought, well, the best place to look for a mine would be to look at the reports next to the mine. So I pulled out a block of reports called the White Williams claims, shown in this blue box here, which is just north of the mine. And in fact, it was immediately south of a block then owned by Western Mining called the Lenser Downs claim. So the final report was written in 1994 by Malcolm Mason of the White Williams claim was that it described it as being too thin. Ultramafic units extend the full length of the option claims and can be equated to the Perseverance ultramafic and the eastern ultramafic bodies of the Perseverance project area. These generally dip steeply westwards, paralleling the Perseverance fault. Exploration was concentrated on the continuation of the Perseverance ultramafic body. A major creek, shown here, runs immediately west of that the ridges, and has quite a lot of alluvial flats with very poor outcrop. All of the outcropping rocks are highly weathered, and ultramafic rocks are often silicified. The area was recommended, it was an option, picked up by Australian Selection, and then nothing much happened until the work was done in 1984. So the purple rocks here are the ultramafics, everything else is sediment in this position here. The location of the hole I mentioned at the beginning of the slide, PT85, is right in this position in here. Now, the claim, so whilst the drilling that had been done within this report in the Persevering ultramafic did find nickel values, they were in fact mostly lithological, and there was no nickel sulphides of note found. Subsequent to that report being written, there have been discoveries made at Rocky Osborne, at Harmony, and then closer to Leinster, close to Perseverance here at Venus. So there have been 3 nickel mines discovered within these 4 little blocks of red-blue claims since 1994. Now, when I first looked at the slides in here, I thought that I would concentrate on the area within this little box, the white box sitting in here. So the blue claims here are the white Williams claims. This white box here covers an enlarged version on the right-hand side here. Overlying the enlarged version is a transparent overlay of the ground magnetics at the time, and you'll see there's double ground magnetic zone through in here. That was a magnetic feature. That drew my attention quite soon to that one there. Okay, so the historical drilling had followed the outcropping ultramafic to the north, which is this zone way over here. But one solitary hole, PT85, is located south of the broad magnetic feature. According to the log, the hole drew entirely in feldspathic quartzite, but my attention was drawn by the geochemistry, which was extremely anomalous, which had used 8 meters at 895 ppm copper and 5,188 ppm nickel. The 1A Gossan, which was nearby at Perseverance, for comparison, has average values of 1,000 ppm copper, only 174 ppm nickel, 1900 ppm chrome, and 62 ppm zinc. Could this in fact be the smoking gun or near miss? So my first field campaign, I realised that the hole of target 9 stone outcrop associated with silicified ultramafic. Initially, I only sampled the silicified ultramafic, so the really silicified portion, as well as a curious triangular quartz pseudomorph shown here as the little purple diagram I mentioned before. It was 100% quartz with a hole in the middle of it. So this is all quartz, and there was just holes through here that had reminded me of what I thought was triangle ore from Perseverance mine. I didn't actually sample the ironstone because it looked to me like laterite. So all the samples, including this one here, came back barren, so I left field break considerably disappointed. When I came back a week later, the situation had changed dramatically. In my absence, Jim Martin, the exploration director of Selection Trust, had subsequently had heard of my exploits, visited the area and sampled the ironstone. The results were extremely anomalous, up to 5,000 ppm nickel, 1,400 ppm copper, 4,000 ppm chrome, and less than 170 ppm zinc, which proved the ironstone to be a true nickel sulphide gossan and not a laterite. In consequence, I was told to quickly map the area and plan a drill program as a percussion rig had already been contracted. Now, the lesson here for people to take away is that I assumed that the outcrop was a laterite. Now, assume is a very interesting 3-part word. Assume can be broken down into makes an ass of you and me. So my recommendation is if it's black and immobile, take a sample for analysis, which is what I should have done. Okay, so looking at the gossan itself, you'll see that there are 2 types of rocks. This is one of the gossans in here. You can see very plainly here that the triangular texture in the silicified ultramafic, with the brown being the limonite after sulphide. And this is the other rocks, the silicified ultramafic, which are also known as knobby peridotite. The area that I've mapped, and this is the first map that I've done, shows the extent of the gossan. Note also the little barbs on either side of the gossan, so it's not a straight line. It's got very cuspate shapes within it. And there's a second little gossan sitting in here. Between the 2 gossans, there's an area here shown in white. These are all rabbit warrens, because what I realised subsequently is when the massive sulphide breaks down, obviously it leaches the metasediment very, very intensely, and all the kaolin is leached away, and it's much, much easier for the rabbits to make their warrens in this much easier leached material. Subsequent to tracing this gossan, when it got to the creek, it was a bit more difficult to follow because it was covered by Wiluna hardpan, but the gossan was able to be traced along the creek for about 1,100 metres to the north. So, comparing the West Fork gossan showing in here with the diamond drill gossan here with the one that I showed you my pet rock at the beginning, you'll see the same texture exposed in all. So this is the triangular texture after bladed metamorphic olivine, which is now serpentine, infill with pyrrhotite and pentlandite. So it's little wonder why the rock that I found when I first visited, it was 100% quartz, didn't give anything in the assay. It was 100% quartz. So there was no reason why it should give any grade. On the left-hand side here, this shows my original map, as I presented in the report that I had to give to justify the drilling budget, and a number of drill sections that I'd proposed. I had initially interpreted this to be a large synform, and just hoped that as I went to the north, drilling on the eastern side, would continue to give me success. Note here also put in a little cross section of the original hole, 85. 85 actually drilled right under the gossan, and this is the zone which is downwards leaching or downwards movement in the regolith of the anomalous values. So here's the 28 meters the 8 meters at 0.5% nickel and 0.1% copper sitting right underneath the gossan. If I'd paid more attention at the barbs that were shown here and remembered back to my time underground at Agnew and the conversation with regard to the fold noses, I would have drawn the sections a little bit differently. So on the right-hand side here is a later section drawn by Western Mining, which shows you how these barbs that you can see that have been mapped in here look in underground drilling. And to finalise, this is what the pit looked like in 2009. This is a fine slide that was loaned to me by Paul During in a presentation of his that's available from the GSWA, and I've turned it around just so you can see the relationship between the lower terrace and the upper terrace with the shapes in the gossan, and for comparison, the figure I've had from the importance of incompetence. So I think you can see here very plainly the shapes that you can see in map view are the same as the shapes you see here in plan view. Okay, now we're going to move to Brazil and talk about the data gap. Now the data gap is where you drill holes in one consistent orientation without drilling any other holes in any other orientation because you're convinced that you understand the geology very, very well. That's also a very wrong thing to do. You need to be aware that if you don't drill holes in the other directions, you won't find what you're not looking for. So often what you're not looking for is very important, as we'll see here was the case at Mirabella. So Mirabella is located in the eastern portion of Brazil, such as the San Francisco Craton here of Brazil. It sits within an area of Paleoproterozoic, mostly granulite facies rocks called the Itabuna Salvador Curaçao origin, which is this pale blue zone, which extends up in here. And the state capital of Bahia State is here is Salvador, right on the coast. So if we zoom in to the Mirabella intrusion in here, I have shown here an analytical signal magnetic map. You see there's a very, very intense, strong feature up in here. These are granulites interbedded with banded iron formation. These are the host rocks. The Mirabella intrusion itself is here, is this area here. If I hadn't drawn it on there, you wouldn't know where it is because it's the low area. It's a very, very weakly magnetic in comparison with the granulite facies rocks in which it's been intruded into. There are two portions of the intrusion that are in fact weakly magnetic. This portion here, which is the liquilateral on top of the dunite, and this portion here, which is a late cross-cutting east-west dike. So the Mirabella intrusion covers 4.1 kilometres northeast by 2.3 kilometres southeast. There's a lobate shape and is divided into a western ultramafic unit and an eastern mafic unit. Santa Rita sulphide horizon is located close to the contact between the ultramafic unit at the base and the overlying mafic unit, which is the top. And as I mentioned, both of those units are cut by a late dolerite dike, which is post-mineral and happens to occupy what we refer to as the type 2 fault orientation. Subsequently, overlying all of this, on top of the dunite, there is what's called the Serra Azul laterite deposit, which is the reason the area was first investigated in the first place. It's a very, very small nickel laterite, so it's never been mined, and it still hasn't been mined. If we look at an east-west cross-section, pre-mined through the intrusion, you see the majority of holes were drilled from the east towards the west at 60 degrees, and proved that the mineralization or the geology is very continuous. You have a basal dunite unit overlain by a peridotite, grading upwards into a pyroxenite and then into gabbro. You notice that on this particular section, 3 faults in blue have been included, have been necessary because of the offsets noted from the drilling in those holes. Notice also that the faults are approximately parallel to the inclination of the drill holes. Now, when we go to look at these, there are 2 types of faults, as I mentioned. The type 2 faults are the ones that parallel the east-west dike. So drilling down a hole, you see it looks about 3 to 4 meters of pegmatite is filling in the zone or in the fault zone, a zone of small faulting either side back into solid rock both sides. However, one of these holes actually drilled down one of these type 1 faults, and you can see that it's absolutely completely trashed. The center of the zone, once again, has pegmatite associated with the fault, surrounded on both sides by a very intense crush zone, down locally to just clay in some places of the zones in here. So when they were picked up in the drilling, they were thought to be, oh, these may be important, they may not be important. The problem was they were quite important when the pit began to be developed. So this is a view of the south wall of the north pit before the failure occurred, and you can see the varying berms here, the 230 bench, 240 bench, the 250 bench, 10-meter benches, and you can see the position of the fault shown in yellow here, and the position of pegmatite that's associated in here. And there's loose material hanging or just sitting above the pegmatite vein. Shortly after this photograph was taken, the wall collapsed. And as you can see, what happened, of course, all the pegmatite and all the weak material around the pegmatite just triggered the collapse of the material, and almost the entirety of the 240 bench was lost. So obviously, once that happened, mining was stopped, and the area was some intense mapping was done. And what was discovered was that there was a very, very common set, a swarm of faults here, about 60 meters apart, continually parallel to the mineralization, to stratigraphy in the zone through in here. And the question became, well, how can we predict these faults in the work that has already been done? So using the existing multi-element geochemistry, in particular the potassium and beryllium, and in some cases sodium analysis, we used to analyze the drill core for zones where those elements were enriched as being possible zones of pegmatite development in cutting through, in the faults cutting through the mafic-ultramafic units. So those zones of the faults, in fact, probably been generated or active during spentonization, as the spentonization front extends away from the fault zones towards the surface and develops this zone of intense faulting. The 2 faults are very plainly shown in here. The main fault, which is the one that's generating these type 1 faults in here, and the type 2 faults shown through here. So this is the orientation of the main fault, which is 57 degrees towards 273. And remember that most of the drill holes are drilled at 60 degrees towards 270. So they're essentially the same. So if you drill it down, if the holes have already been drilled here, the chance of missing these faults, as has happened, is extremely high. Now, while we're on the topic of spentonization, I've put together this slide to show you some interesting anomalies that people get excited about, where in fact they aren't in fact indicative of mineralization. The first slide shows that on top of the hill here, you get a nickel laterite developed. So that's fine. And the nickel sulphide is actually halfway down the slope towards the bottom of the hill, which is the gabbro. So if you use just topography here, you'd find the nickel laterite. The second slide shows the geology, as I've mentioned before. The third slide shows the analytical signal magnetics, once again showing you the area here of weakly magnetic developed on top of the nickel laterite. This slide is particularly interesting because many people would state that serpentinized dunites don't give an IP anomaly. For those people, I would say you're completely wrong, because secondary magnetite is a wonderful IP generator. As you can see in here, the top of this hill is just 100% conductive. in terms of IP chargeability. A very small EM survey was also done, and we generated a small EM anomaly sitting in here, which was subsequently certainly proven not to be generated by sulphides. Then the IP conductors, this one up in here was actually due to a footwall zone of iron formation outside of the intrusion. And the last one, and perhaps most importantly, one in here is the gravity. A very dense gravity survey was done over the whole intrusion, and as you can see, the top of the hill where this pentonized dunite occurs is a great gravity low, not a gravity high, as many would expect to happen for an ultramafic. So, what's the effect of pentonization? This slide, put together by Doug Cook, shows it quite nicely. Now, for Mirabella, we had petrology done on almost every hole at a very routine downhole depth. So we had 549 petrographic descriptions. From each of those, Doug derived what he called a pentonization factor, which is where he divided the percentage in description of pentine over serpentine plus olivine by 100%. So that's the quantity of the olivine that's been transformed into serpentine. So plotting it here, you can see that towards the top, no surprises there, that's where the nickel laterite sits, the highest pentonization, and as you go down, it decreases quite markedly till you get to the zone at the bottom where it's less pentonization. The color in the background here is density. So this is fresh dunite in here, little serpentinization. Up here it's 100% serpentinized. So you can see the change in color is exactly proportional also to the degree of pentonization. On the right-hand side, the same image against downhole magnetic susceptibility. In the serpentinized part of the ultramafic, very, very intensely magnetic, but lesser magnetic in the fresh rock. So just things to be aware of. Not always are ultramafics dense and heavy rocks and strongly magnetic. They can be, in fact, quite different. So the last example I want to cover just shows you about the necessary, or the reason you need to find some kind of outcrop if you're having a lot of difficulty understanding what's the data you're getting from drill hole structure. In the Carajás region of Brazil, it's a jungle conditions. There is very little outcrop, and therefore, if you've only got drill hole structure to use to work out the structure, you need to understand what that's telling you. In some cases, as we'll see here, we actually needed to create outcrop to try and understand what was going on. So where we're looking here in the Carajás region. The Carajás region is this area here, the block B, which is this diagram in here, and the Carajás domain sits in here on the northern edge, or the southern edge of the Guiana Shield, coming in here. Mirabella was over here, so now we're coming inboard in here. Within the area here, Jaguar sits in this position down in here. This is the main portion of the Carajás province. All the red squares here are IOCG deposits. So Lobo in here, coming down here to the Siqueira and Sossego in the area through here. All the iron mines are shown in the well, they're not shown at all, the iron mines. The iron mines fit in this area through here and also through in here. So it's a very, very heavily endowed and strongly endowed area. Jaguar itself sits at the intersection of this McCandless fault and this Canaan shear zone coming through in here. And it is located very, very close to these two blue intrusions, which are in fact the Neo-Archean Puma and Onset layered ultramafic complexes. And the point to take away from this slide, in fact, in terms of context, is this anastomosing fault network that you see well and truly develop in here. So you've got faults coming this way, faults coming that way, faults coming this way, all intersecting at very low angles, acute angles in the zone through in here. This is very important for the understanding of Jaguar itself. This is a map from mapping of the Jaguar prospect itself. The pink color in the background is the host granite gneiss, which is Mesoarchean, so 2.96 gigayears old. The mineralization at Jaguar is hosted by a dacite, which is dated at 2.7. So this is the same age as the iron formations at Carajás. It's exactly the same age. So a Neo-Archean age. And the mineralization is located in shear zones. These red zones through here are the mineralization zones. Here, hosted within dacite. Up here at Onça Preta, Twister, and Onça Rosa, hosted within the granite gneiss. And Tigre is hosted similarly also within the dacite. Mineralization is hosted by dacite porphyries, granite dacite contacts, granite, intrusive dolerite, and ultramafic lenses. The main alteration minerals, so quartz and dacite, and that's when you're near the main mineralisation. As you get further away, the alteration is biotite, chlorite, actinolite, talc, and at great distance, your albite, case, feldspar. And the sulphides, this is interesting here because they're very high tenor sulphides, are millerite and pentlandite, and the secondary nickel sulphides, volarite, thalidomite, and vasite, with lesser pyrite, pyrrhotite, chalcopyrite, and silarite. This is a map here now showing nickel in soil. So, and you'll notice once again this very, very intense pattern showing these two fault directions, harking back to the idea here of these anastomosing cleavages. So the blue zones here are in fact conductor plates. So the principal tool for discovery of more nickel sulfides at Jaguar has been the use of downhole EM. What I've shown here is a little long section through the Onça Preta deposit here, showing the varying plates in colour and their orientation as interpreted by a geophysicist, as distinct from the downhole lineation of the plunger mineralisation measured in drill core. As you can see, the two are exactly the same. Jaguar is the only nickel occurrence I have worked at whereby if you get a downhole EM plate, you can guarantee that it's sulphide, and more so, you can guarantee that the sulphide is nickel mineralised. So it's a 100% success rate. That's very unusual for nickel sulfides. Now, the problem with drilling and the number of intersections at Jaguar, so this shows what the intersection looks like. The 4 holes are drilled, and these are intersections of nickel sulfide. How do I connect those? Is it an on-echelon array like this? Is it an on-relays array like this? Or is it one simple folded layer? Now, in the absence of any outcrop, you've got to make a call because you're trying to work out what the mineralisation is. But this is vitally important for production of an ore body later on, and for the ore resource. You need to have some confidence in what's going on. So you would think that oriented drill core would in fact be of use. The problem with the oriented drill core that we inherited from Valley when we took on the project in 2019 is that, as you can see here, I've separated it into the holes that were drilling towards the north, and that's the average hole orientation, and the holes that drilled towards the south, and that's the average orientation. You can see that almost all of the data fits within these concentric rings around the average drill hole orientation, which means nothing more than that the data here is useless, and it's all pretty much reflecting core spin and or very poor orientation procedures. So the lesson to be taken, and when we drilled down into that was in fact the case. There was nobody supervising the people that were marking the core. So the lesson here is, if you wanted to get core orientation, you want to guarantee core orientation of your drill core, you need to have someone who knows what they're doing, and you need to supervise the orientation of the core marking. 3 years later, we came back and we got some reliably oriented core. Now, only 61% of the core was in fact they're able to get orientation marking on that, and only a smaller portion of that was in fact successful. And so at the end of the day, we only have 16% of all the core which can be able to be used as in terms of reliable orientation directions. If I was to use just the high quality of those ones, it comes down to 7% only. So you've only got 7% of your drill core which will enable you to make a prediction on what the ore body looks like. That being said, you can see that the majority of orientations are subvertical in this zone through here, and in fact the sulphide and magnetite veins follow the same orientation. The lineation is actually subvertical in the zones through here, as indeed are the sulphide lineations. So we know straight away that we're looking at a very, very subvertical feature, and with a plunge direction which are quite steep to, in some cases, moderate in through in here. Problem is that's fine, but how do we relate that? What is the importance of the foliations? So in 2023, I hosted a visit from 2 professors here from the University in Brasilia, structural geologists, to try and understand what was going on, as well as the ore reserve geologist for Centaurus, Laurie Barnes. And I asked the people on site, and we carefully selected some of the drill cuttings that have been used, and I said for them to please clean up the walls of those drill cuttings so we could get a look at what was happening. What you can see here is the main foliation shown in black between the dacite, SVAP is dacite in Portuguese, was subvolcanic acid porphyry, and granite coming in here. And you notice also that there is a persistent, although not as well developed, almost sub-horizontal shallow dipping cleavage, which you thought initially was a kink band. through in here. The main cleavage direction is this one here, very, very steep towards the west, towards the north. This outcrop, however, was the outcrop that really gave us away. This was the outcrop that really made everything click and we could understand what was happening. So on the left-hand side here, it shows the outcrop before it was washed, and about 10 metres to the left-hand side of where the yellow arrow is, there's a drill collar, and the hole drills underneath this outcrop that's in here. At the position where my pointer is here, it adheres to nickel sulphide, which is the reason why this drill collar was, well, the reason why the platform was extended into here to cut the outcrop. This is the outcrop, this is what it looks like, and we're going to look now at that cross-section on the next slide. So this is what it looks like in close-up. You can see the boudin necks plunge towards very, very shallowly towards the east, to about 10 metres high, about 4 metres wide, and all the red here is massive sulphide. So there's outcropping massive sulphide with blocks and boudins here of dacite within the middle. In some of these cases, the massive sulphide split, and there's massive sulphide going through this, and in a lot of most cases within the massive sulphide, there are rootless folds and there are fragments of the subvolcanic acid porphyry in this zone in here. So straight away we began to think, what is the model that might be causing this? And some of the ideas were shown over on the right-hand side in here of intense pure shear, intense shortening, developing this two-dimensional chocolate tablet boudinage. So this is the model we came up with from that outcrop, and compared to a model here of an LS tectonite. Remember what we saw on that slide of the drill platform. That's what we saw on the slide of the drill platform. That's what we see we look down the plan view as well. So it looks as if the SVAP had been intruded by shears that was strongly compressed and developed boudinage in two directions. Begin to be pulled apart, the sulphides flowed into the internal zones in here. What was interesting here is that this, what we termed secondary foliation in the neck folds in here, which are shown here at AH, is only a very locally developed feature. You can see this in the drill core, but you don't realise that they're not pervasive. The pervasive is the main myelinic foliation. These are just local features and have no real consequence in the whole affair. The problem is that when the logging was done, they were all described as foliation. So if I'm plotting this foliation and this foliation, clearly this is the important one, this one's not important. And these are the ones that give you a lot of fluff or a lot of noise on the stereo plots. So in the end, the model we come up with is this one in here, intense north-south shortening, which with a small simple shear component gives you this development of these strong cleavages that are strong foliations that are anastomosing, and the sulphide is forced to come vertically up in this vertical feature coming through in here. So that's what I had to tell you. What are the lessons that I take away from that? Firstly, as I mentioned before, I believe context is everything. If you don't understand the controls of your target, then you need to understand the regional setting. And remember that geology is fractal. What you see at a large scale, as I hope you've seen in this presentation, can be carried down to the very finest scale. Don't forget that, it's very important. The next thing is important to hone your observation skills. A common saying is the best geologists have seen the most rocks, and I have no doubt that is the case. The more you see, the more you learn, the more you store away in your memory, and the more you have cause to come back and use that later on. As I've mentioned, it would be nice if we could try and harness the little clues when the memory bell starts to ring in, or at least record them so you can revisit them later. Either do that using a digital camera or smartphone to record outcrop and core for later analysis, and if you don't understand what's going on, send those photos to someone that might know to get a second opinion. Sample constantly. The big lesson we get from artificial intelligence is that pattern recognition pays. The one thing we don't get from artificial intelligence is that the context, i.e. that is a right brain activity, and that's strictly a human trait. Computers can't do that for us. So the day-to-day detailed material can be well identified by artificial intelligence, but we need to step back all the time to understand the big patterns, the context. So you need to be inquisitive and creative. So you need to back yourself. This is good for young students. You need to get in there and not be afraid of making an opinion. Giving an opinion, even if you don't understand what's going on, because the only way of learning is by inventing an opinion and being and being advised whether it's correct or not. Remember that nobody has a mortgage on the truth. You must ensure, however, that you can support your hypotheses with facts and or solid reasoning. So you should always work with at least 2 hypotheses to give yourself an alternative if your favoured model fails. As I showed from the example in Brazil, if there is no outcrop, be creative and find a way to create some. Obviously, we were lucky. We were drilling in an area, we had a lot of equipment available, and we already had a number of drill pads that had been created. So we weren't doing any additional damage to the environment, just cleaning up the damage that had already been done. That will be mined once the mine is gone. And key of all of these things is persistent pays. The role of teamwork within geology is fundamental. Science is cumulative and mostly well documented. You must always, however, seek out the original articles because over the passage of time, varying authors will use the original data for their own means. So you need to go back to the original articles and find out what was written in the first case. And you shouldn't be afraid to stand on the shoulders of those who have been before you. Better still, ask them for advice. So I recommend that you enjoy exploration and the passionate pursuit of knowledge, but always remember that knowledge not shared is knowledge lost. Thanks very much.
That was awesome. Thank you so much for that, Rocky.